Hello, this is Professor Dan Kernler again, and this is our second video in section 16.5 looking at triple integrals in cylindrical and spherical coordinates. In this video, we're going to be learning the cylindrical and spherical forms for triple integrals and then doing one example of each. Also having a little fun with a new green screen, so we'll see how that goes. First, let's start with cylindrical triple integrals. Essentially here, if we look at a representative piece, I don't know if I can draw like a three-dimensional version of this. We want to find the volume of that representative piece. That's just terrible. Let's try drawing it from the side. And it's a little bit skewed, but it is essentially a box. It's a length times width times height. So if we look at its dimensions, the change in radius is the length of the box. The height will be the z. And then the width of it is these two arcs. Now if we just kind of go in the middle, this is an arc length formula, which is the radius times the angle, which in here would be the delta theta. So the volume of this representative piece is, let's see, delta r times z times r delta theta, or z r, nope, not z, delta z, delta, change in z, not the actual z, but how much the z has changed. So it would be r delta z delta r delta theta. And so if we put that into cylindrical coordinates, this triple integral of a function dv in terms of x, y, and z becomes the triple integral of a function of r cosine theta instead of x, and r sine theta instead of y, and then z. And then we have r dz dr d theta. And then z goes from, on our graph there, from c to d. That's the z. R goes from, we're going to use A to B. And then we're going to use alpha to beta for the angles. So you have your function, and then the dv becomes basically from polar coordinates r dr d theta times z. Let's try an example here. We're going to set up a triple integral involving cylindrical coordinates that finds the volume of the solid bounded by this paraboloid below the plane. So I think we have talked about one like this before. This is like the slice of my thumb, silly example. X, Y, Z. And you have y, 1 minus x squared, or 1 minus y squared. Yeah, 1 minus x squared, 1 minus y squared. And then you get a circle, and then you're slicing a plane through the side here, and you end up with just this little portion right here. That is totally illegible. Let's try an actual graphic of it. There's a drawing of it in Maple. That looks a little bit better. So there's the paraboloid, and then our plane, and then we're slicing off just the top of the plane. Incidentally, if we look from the top, it kind of looks circular. We will come back to that in a little bit. Okay, so we want to find the volume, and the volume will be the triple integral dv over the region. And so what we're going to do instead is we're going to try to write this in terms of cylindrical coordinates. Okay, so this will be a triple integral, and we're going to have our r dz dr d theta. Now z goes from the bottom one to the top. The bottom is the plane, 1 minus y to the top, 1 minus x squared minus y squared. Now there's a problem there. Your bounds are in terms of x and y, but you're integrating in the cylindrical coordinates, so we will have to fix that. For the rest of it, we really need to figure out what the region is in the xy plane. So let's look to see where these two curves intersect. 1 minus x squared minus y squared equals 1 minus y. Let's see here. Let's add x squared plus y squared. And then I guess equals y, which is kind of a weird thing. We could do some algebra with that. you could notice there x squared plus y squared minus y equals 0. If we complete the square on that, x squared plus y squared minus y, we add, what would we add? We'd add a fourth equals a fourth. That would give us x squared plus y minus 1/2 squared equals 1/2 squared. And it's a circle radius too. But we want polar coordinates. So let's actually go back up. Not a circle radius 2, circle radius 1/2. X squared plus y squared equals y. Well, x squared plus y squared is r squared. And y is r sine theta. And so if we subtract r sine theta, we get equals 0. Factor out an r. So we either get the origin, r equals 0, or r equals sine theta. That's where they intersect. So both of those are actually the same circle, r equals sine theta. You can graph that. I actually have it up on Desmos right now, and I'll pull that up, but you might want to know where it comes from. So think about sine of 0 is 0. Sine of pi over 4 is square root of 2 over 2. Sine of pi over 2 is 1. Sine of, oops, I kind of got off there, but that's all right, is 1. Sine of 3 pi over 4 would also be square root of 2 over 2. And it kind of moves around like so. After that, the r gets negative. So as you sweep into like 5 pi over 4, it would be, r would be negative square root of 2 over 2. And so it would actually give you the same point. But I do have a Desmos graph up here. Let's try this one. Desmos actually really easy to graph polar coordinates. You can type r equals sine theta, and look, there you go. There's your circle radius 1/2, centered up here at 0, 1/2. Okay, so why is that valuable? Well, we can see now that r, we're just going to integrate from 0 out to the circle. From 0 out to the circle as we go through here. So r goes from 0 to sine theta. And then theta only goes from 0 to pi. We don't want to keep going because that will wrap and do the circle twice. We're just going to go 0 to pi. So this is pretty close. The last thing we need to do here is we need to fix the x squared minus y squared and the y, because they have to be in terms of r and theta. So let's rewrite this. 0 to pi, integral 0 to sine theta. And then y is r sine theta. And we could call that 1 minus r squared, right? If you factor out a negative 1, it's x squared plus y squared. And then we have r dz dr d theta. So that would be our integral in cylindrical coordinates. Okay, moving on. All right, next let's take a stab at the triple integrals in spherical coordinates. These are a little more challenging to visualize if the last one wasn't challenging enough. So I have this open source visual here that I kind of stole. I do have it sourced here. But there's a couple of errors with it, so I want to address those first, and then we'll fix it and try to visualize what this volume of this representative piece is. First, you see when we pull it out, it is essentially, it's similar to last time. It has some angled sides, but it's essentially a box, roughly. So we're going to try to find it just length times width times height. There's a couple of these that are easier than others. First, let's pick a representative point here on the corner, and we have the radius rho out to that corner. And so when the angle phi sweeps vertically, then the height of this box is going to be rho delta phi. You can see here on, like above rho where it's got this delta phi, that's actually just phi, not the change in phi, that's the actual angle phi. Second, let me actually label below that, that's phi. Second, we have, let's see, what was I going to do next? We have the change in radius is relatively straightforward. That would be this dimension. So that would be delta rho. Okay, so far so good. It's that third side that is the most challenging. This one over here. That one's the most challenging. The key there for that one is to imagine you're putting a line perpendicular to the z-axis at the level of your corner point there. You have the angle phi from the positive z-axis, and so this over here would be rho sine phi. And so that's the distance to that corner, and then theta is sweeping out in the xy plane. And so the distance across here would be rho sine phi times delta theta. And that's this guy here, which is actually represented by like one of these bottom ones. And so what you end up with after all that, though, is this crazy, pretty crazy expression here that you're going to want to make a good note of, that in spherical coordinates, your triple integral over the region becomes a triple integral in spherical coordinates f of, and then if we do the conversion, instead of x, y, z, it's rho sine phi cosine theta, rho sine phi sine theta, and then rho cosine phi. And then it's rho squared sine phi d rho d phi d theta. And then it would go from rho 1 to rho 2, and then phi 1 to phi 2, and theta 1 to theta 2. Okay, let's do one example of this, and then we'll call this video, and then we have a couple of additional examples after this. We're going to try to find the volume of this ellipsoid, x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. This one would be pretty challenging with rectangular coordinates. You'd have to solve for z. You'd have a square root to a square root. I guess you could just do the first octant again, where you'd have all these square roots of stuff. The spherical seems like it would be maybe not much better. However, we're going to do a little substitution. We're going to do u is equal to x over a, v equals y over b, and then w equals z over c. And you can see why we would choose those. X is then u, or a times u, and y is equal to b times v, and z is equal to c times w. And so then dx is a dw, dy is b dv, and dz is c dw. Doing like a triple substitution. The volume then, which would be the triple integral over the region d, dz, dy, dx, now becomes the triple integral over this new region, but dz is c dw. We'll call it d1. So dz is c dw. Dy is b dv, the b and c are constants, and then dx is a du. But let's look at what the region is. If we do that substitution, it's just u squared plus v squared plus w squared equals 1. So in spherical coordinates, this integral, ignoring the ABC now, just the triple integral over this region, whatever this new region is, dw, dv, du, is simply the integral over a sphere radius 1. So that would be a, b, c times the triple integral of a sphere radius 1. So rho, we're going to do a triple integral of, in spherical coordinates, sine phi d rho d phi d theta. And then rho, it's a radius 1, is going to go from 0 to 1. We're going to do a sphere. Phi is going to go from 0 to pi. And then we need to go all the way around, so theta goes from 0 to 2 pi. Okay. And looks like a rough integral, but actually isn't too bad. We're integrating rho first, so we get 1/3 rho cubed sine phi. Actually, let's go 1/3 rho cubed from 0 to 1, and then the sine phi d theta We have a, b, c, integral from 0 to 2 pi, integral from 0 to pi, that would just be 1/3 times sine phi d theta. We can pull the 1/3 a, b, c out in front. Integral from 0 to 2 pi, and then we're just integrating sine phi d phi, so that's negative cosine phi from 0 to pi d theta. That's 1/3 a, b, c, integral from 0 to 2 pi. Negative, let's see, cosine of pi is -1 minus 1, so it looks like we get 2 d theta, so that's 2/3 now, a, b, c, integral from 0 to 2 pi d theta. That means we're just going to multiply by 2 pi. And so we end up with 4/3 pi a, b, c is the volume of that ellipsoid. I feel like I need to catch my breath after that. That's it for this video. We're going to have one more video in this section, and we will do some additional examples in this one. But that is it for this video.